Okay, welcome ladies and gentlemen to 2.6, looking at complex zeros. So we're going to be looking at the big fundamental theorem of algebra. We're going to look at complex zeros, and we're going to be looking at factoring. So let's first start off with the fundamental theorem of algebra. Fundamental means basic. It's the most basic thing. It's something that's super, super important. And what this is basically saying is if you have any polynomial where the degree of that polynomial is bigger than 0, so like x to the first power, x to the second, x to the third, whatever the degree of the polynomial is, some of these it has n number of zeros. So if I had x to the third power as my degree, 3, that tells me I have 3 zeros. So, oops. That's basically the fundamental theorem. If I gave you the function x cubed plus 7x minus 3, you're guaranteed 3 zeros. Basically saying something that makes this thing equal to 0. Now, some of them might be repeated, some of them might be real, and some of them might be imaginary or complex. Some of them might be rational, some might be irrational. Doesn't matter what type of number they are, you're guaranteed 3 of them. And here's how linear factorization theorem looks like. If you have this polynomial, then it has n linear factors. So if we were to give you a quadratic that said x squared plus 6x plus 8, this will have exactly 2 factors. In this particular case, it's x plus 2 and x minus 2. Sorry, x plus 2 and x plus 4. Not paying attention to myself here. All right, so x plus 2 and x plus 4. Likewise, x squared plus 9 also can be factored to 2 different factors. Now, some of you are thinking, well, that doesn't factor because you told us it doesn't factor. Well, you're right. It doesn't factor with real numbers. But if you think about what makes x squared plus 9 equal to 0, you would get x squared equals negative 9, and that means x is equal to plus or minus square root of negative 9 is 3i, which means I can write this as a factored form of x plus 3i and x minus 3i. So you notice this x squared plus 9 can still factor to x plus 3i and x minus 3i. We could get things like this: x plus root 2 and x minus root 2. Things like that, that's still a factored form for a polynomial. Now what this is saying is if you have a polynomial with a third degree, you're going to have 3 factors. Or fourth degree, you're going to have 4 factors. And those factors look like this. These z1, z2, all the way down to zn, those are our complex zeros. You have to remember complex zeros are any zeros. They can be real numbers or fractions or decimals or anything. But remember, complex numbers, the number 3 is the same thing as 3 plus 0i. So it's still a complex number. A is called our leading coefficient. So whatever the leading coefficient is, that's going to go in the front there. And we're going to use all of this to either create a polynomial or factor a large polynomial. So let's look at this first. If I was to write this function for you and I said write it in standard form, that means I'm going to write this as, okay, let's FOIL this. I get x squared minus 2xi plus 2xi minus 4i squared, which when simplified, this becomes x squared. Well, minus 4i squared is a plus 4, and notice the centers go away, so it's a plus 4. So this is the standard form for this polynomial. And the zeros are negative 2i and positive 2i. Those are my zeros. However, since these are imaginary, there are no x-intercepts. And if you think about the function x squared plus 4, it looks like this. And there's obviously no x-intercepts on that particular function. But we can look at ones like this. A little bit more, and if you think about this, there are 3 factors, which means my answer is going to be a cubic. And what I like to do is I like to take care of the ugly ones first. If I FOIL these things together, I get x squared minus I root 2x, right? This piece times this piece, plus I root 2x, minus, okay, root 2 times root 2 is 2. I times I is I squared. And I simplify that down to x squared plus 2. All right? But I didn't do anything with that x minus 5 yet. So I have to keep that going. So I have to FOIL here. X times x squared is x cubed. Minus 5 and x squared is minus 5x squared. X and 2 is 2x. And negative 5 and 2 make negative 10. So there we have a polynomial of degree 3 with the given 3 factors from our polynomial. Oh, I didn't answer the rest of the questions. The zeros are 5 and plus or minus I root 2. And the only x-intercept is the coordinate 5, 0. That's my x-intercept. Because the other ones are imaginary, they're not actual x-intercepts. And the same goes for this one. When you are looking at this particular problem, don't do the first one times the second one, then times the third one, then times the fourth one. Do them separately. Do the good ones together. So I get x squared minus 6x plus 9. And then here, I get x squared, and you notice the outer and the inners, they go away. I get minus I squared, which becomes a plus 1. And then I can multiply this way. I have to take this x squared, I have to multiply to all pieces, so x to the 4th minus 6x squared plus 9x, sorry, 6x cubed plus 9x squared plus x squared minus 6x plus 9 when I take the 1 and multiply by all 3 things. And I get x to the 4th minus 6x cubed plus 10x squared minus 6x plus 9. So there we have our quartic. The zeros of this polynomial are positive 3, positive I, and negative I, but the only x-intercept for the graph is positive 3. So one of the theorems kind of things that we're going to get here is complex conjugate zeros. If one of your zeros is a plus bi, then its conjugate is absolutely going to be another 0. And you notice all 3 of these problems here. I get x minus 2i, x plus 2i. Those are conjugates, the negative 2i and the positive 2i. Plus and minus I root 2, those are conjugates. Plus and minus I, those are conjugates. We can look at ones like this. X minus 2 plus I and x minus 2 minus I. These are the zeros of 2 plus I and 2 minus I. Notice they are conjugates. So basically saying if 3 plus 2i, or whatever you want to say, is a 0 of the function, then so is, by definition here, 3 minus 2i. The reason that comes up is this. if you wanted to write a polynomial with a minimum degree in standard form, we could write, using these factors, we could write the factors and then multiply to find the polynomial. So we're going to do that here. The negative 3 means it's x plus 3. The positive 4 means it's x minus 4. And then we have x minus 2 minus I, but you have to include x minus 2 plus I. And let's think about how to multiply those two things together. We don't worry about these. We will in your actual answers, but right now let's deal with these two things right here. And there's something that I like to do with this. I like to switch the parentheses around. I have x minus 2 plus I by distributing that minus in. And we have x minus 2 minus I, again, by distributing that minus sign in. And if I think about this as x minus 2 plus I and x minus 2 minus I, so all I've done is rearrange the parentheses in such a way that now I have conjugates. I have a plus I and a minus I, which means when I FOIL, I get x minus 2 times x minus 2, that's my first and my first, minus, my outers is minus I times x minus 2. I have a plus I times x minus 2. And I get plus I and minus I makes minus I squared. Now notice that this and this cancel, and here I get x squared minus 4x plus 4. That's gone, and this becomes a plus 1. And we could use that and multiply by whatever we would have gotten here. All right, so I really wanted to show you how to write this here. Notice when it says minimum degree, don't start adding extra zeros to this problem. Don't do x plus 3 to the second power or x minus 4 to the third. You're just making more and more work for yourself. Now, if I was to want to find all real zeros, this is what we've been leading up to for the last couple lessons. You need to list out your possible rational roots. And you need to remember that P is all of my factors of 8. So it's plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So those are my possibles for P, and then Q are plus or minus 1, which means this is my list of possible rational roots. So then you're going to do synthetic division all the way down. Notice this is x to the 5th power. You might or probably will get 4 or 3 of these. You need to go all the way down to a quadratic before you're allowed to do anything else. So you're going to have to test 3 different, or you have to get 3 different real zeros or rational zeros here. Once you get to a quadratic, you can either factor or use quadratic formula. So kind of sink that into your thoughts just a little bit. And you can kind of look at the graph. If you look at the graph, you'll see that there are 3 real zeros, and they are kind of nice numbers. So if you did synthetic division, you would notice that you get x plus 2, x minus 1, and x minus 4. You'll notice that those are the three good numbers, and they all came from this list right here. But what is left over is x squared plus 1. Well, this piece right here will factor to x plus I and x minus I, as I talked about before with the x squared plus 9 towards the beginning of the lesson. So there's the linear factorization. X plus 2, x minus 1, x minus 4, and x plus I and x minus I. That's the linear factorization. All 5 factors for this quintic function. Oh, I do want to kind of go over this particular problem. When I give you a 0 of x or 1 minus 2i, that means using the same logic as before, 1 plus 2i is also a 0. So we can say this is x minus 1 minus 2i and x minus 1 plus 2i. And we can factor, or not factor, we can FOIL here. X minus 1 times x minus 1 is x squared minus 2x plus 1. That's the first. Now remember, the inner and the outer are going to cancel, so then on the lasts, I get a minus 4i squared, which is really plus 4. So this becomes x squared minus 2x plus 5. So that would be this term. That would be here. If I wanted to find the remaining zeros, all I would have to do is take this quartic function. I would take f of x here, and I would do long division for x squared minus 2x plus 5. We're saying, I already told you that x minus 2i and x plus 2i are zeros, and therefore this will have 0 as a remainder. So when you do this division, you're going to be left with a quadratic. In this case, it would be 4x squared plus blah, 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 which you can then factor or use quadratic formula. Which I think this starts to get pretty handy. It gets to start pretty cool here. I like doing this stuff with polynomials. I know it's a little bit tedious, but the final product should get you kind of enthused a little bit there. Now, every once in a while you do get a problem like this as a product of linear and irreducible quadratic factors with real coefficients. So as you went to factor this problem, you will see, using your possible rational roots, quite sadly maybe to some people, you'll get this problem where it's x minus 2/3. You'll notice that 2/3 is your first rational 0. And then you're left with 3 x to the 4th plus 6x squared minus 24, which you could factor out of 3, and depending on where you want to put it, I kind of like to put it right here. I can take out a 3 here, right? 3, 6, and 24. I can factor that out. I'd be left with x to the 4th plus 2x squared minus 8. And as we continue this process, remember synthetic division for this 2/3, by the way. We get 3x minus 2, and we get here x to the 4th plus 2x squared minus 8 actually factors to x squared plus 4 and x squared minus 2. Which I know we can factor one way or the other, but sometimes the book likes to call these things irreducible quadratic factors. Oops. 3x, oh, that was ugly. 3x minus 2. X squared minus 2 will factor to x plus radical 2 and x minus radical 2. And then x squared plus 4, they're going to call it an irreducible quadratic factor, even though we know how to factor it. What we really want here is just real numbers sometimes. All depends on the problem that being asked. So write f of x as a product of linear and irreducible quadratic factors, each with real coefficients. So in this case, everything here is real, no imaginary values. But if it was to ask you to fully factor to all the entire linear factorization, we would factor this x squared plus 4 into x plus 2i and x minus 2i. Looky there, that's it. That's going to be finishing off there for 2.6. I hope you guys learned a little bit of stuff, and I will see you guys tomorrow.